Hello everyone and welcome back to Brake Particle Emission. Today we are moving from the road to the lab to talk about one of the most critical tools in the fight to understand and reduce brake wear. With regulations like Euro 7 focusing on non-exhaust emissions, we need precise ways to measure them. That's where the Nanovea T50 pin-on-disc tribometer comes in. In this video, we will break down exactly what this machine is and how it helps us simulate and analyze the very particles my channel is all about. Let's get started. Before we look at the Nanovea T50 specifically, let's understand the basic principle. A pin-on-disc tribometer is at its heart a simulator. It recreates the fundamental event of braking in a highly controlled laboratory environment. The pin is a small sample of the brake pad material, and the disc is a sample of the brake disc material. A controlled load is applied, pushing the pin onto the disc, just like your brake caliper squeezes the pad onto the rotor. The disc then rotates, creating the sliding friction that we know generates heat, wear, and ultimately particles. This simple setup allows researchers to isolate the friction pair from all the other complexities of a full brake system and study it with incredible precision. Here, the figure 1 shows a schematic illustration of a basic pin-on-disc tribometer. Now comes the working principle. The pin-on-disc configuration is one of the most widely used tribological test methods. During the test, the pin presses against a rotating disc under a set load and speed. The tribometer measures the coefficient of friction, wear rate, and wear track development on the disc. This method works for coatings, bulk materials, ceramics, plastics, and more. Now, for the exciting part, the data. Once we run a test on the T50, we get a wealth of information. First, we get a live friction coefficient graph. This tells us the stability and performance of the material pairing. A stable graph is good. A noisy one can indicate problems. After the test, we use profilometers to measure the exact wear rate of both the pin and the disc. We can see the 3D profile of the wear track. This is the tangible evidence of material loss. And most importantly, by weighting the samples before and after and by using particle samplers, we can calculate a particle emission factor. This is a critical number that tells us for a given set of conditions how many milligrams or even billions of particles are emitted per kilometer slid. This is the direct input for environmental models and regulatory standards. So, how does all this lab work translate to the real world? The data from the Nanovea T50 is the foundation for progress. Material scientists use this data to design new, low-wear brake pad formulations, whether they are non-asbestos organic, ceramic, or something entirely new. They can quickly test dozens of recipes in the lab before ever building a full-scale prototype. This research is directly feeding into regulations like Euro 7, which aims to set limits on brake particle emission for the first time. The T50 helps define those limits and gives manufacturers a tool to meet them. Ultimately, by understanding the fundamental wear mechanisms at this microscale, we can develop the technologies needed to significantly reduce the contribution of brakes to urban air pollution. It's a perfect example of how precise laboratory science leads to a cleaner, healthier environment for everyone. Thank you for watching. If you have questions about the T50 pin-on-disc tribometer or brake particles in general, leave them in the comments below. Don't forget to like and subscribe for more content on the science behind brake emissions. See you in the next video. Till then, bye-bye.